A telescoping series is an interesting kind of series because if you actually write out the terms of the sequence, you'll see that when you calculate the series, the terms of the sequence, there's a bunch of them that cancel out, and therefore you can actually just add a few fractions together that remain and get the value of what the series converges to. So it's going to be something of the form, the sum n going from 1 to infinity of b sub n minus b sub n plus 1. So you have two generally fractions that are subtracted. So the subtraction is where the cancellation happens, and they're very similar in form. So for instance, if you think about the series n equals 1 to infinity of 1 over n times the quantity n plus 1. So we looked at this series earlier and we saw that it converged. I think we also calculated what it converged to, and if I remember correctly, that was equal to 1. But let's look at this in a different way. Another hint I'll give you here is a lot of times when a telescoping series, can be used, you'll often need to do some partial fraction decomposition to start with, but it's usually fairly straightforward partial fraction decomp. So let's take a look at this fraction, and I'm going to do partial fractions on that. So I have 1 over n times n plus 1. And it might be a minute since we've done this, so just as a refresher, you take the factors of the denominator and put a constant over each separate linear factor. And you have to solve for what those constants are. All right, so we can do that, starting off by multiplying everything through by the least common denominator, which would give me 1 equals a times n, or a over n times n plus 1 would be a times n plus 1, because the n's would cancel, and then I would have b times n because the n plus 1's would cancel. Okay, and if we choose some strategic values for n, say n equals 0, I would get, say, 1 equals a times 1, so we learned very quickly that a would be needing to equal 1. And when n equals 1, actually not 1, but negative 1, I would have 1 equals, the first term would cancel out to 0, and then I would have b times negative 1. So b equals negative 1. All right, so that means my sum can now be written as n going from 1 to infinity of 1 over n minus 1 over n plus 1. And now you can see it being in the form b sub n minus b sub n plus 1. And here's what happens. There's nothing special to evaluating a telescoping series. You just write out a few terms until you start seeing what's going to happen in general. So the sum of the first n terms would be, starting with n equals 1, that would be 1 over 1, which is 1. All right, then when n is equal to 2, or actually, sorry, I have another part to my n equals 1 because it's 2 terms. So minus 1 over 1 plus 1, which would be 1/2. So that's everything that happens when n equals 1. Plus, the next term, when n is equal to 2, would be 1 over 2 minus 1 over 3. And then when n is equal to 3, and usually this pattern reveals itself pretty quickly, 1/3 plus, minus 1/4. And we could continue, but I think I already see the pattern. So for instance, I have a negative 1/2 and a positive 1/2 here. A negative 1/3 and a positive 1/3. And I have a negative 1/4 in this term, but since it's an infinite sequence, I'm going to have another one, positive 1/4, on the next one to cancel with. So these will all eventually cancel, leaving me just the value 1. And that's how we evaluate a telescoping series. Let's try it again with a different example. All right, so it needs to be written as effectively two fractions that are subtracted from one another. So let's start off writing it in that form. So using partial fractions, I would have 2 over n times n plus 2, and that's going to equal some constant over n plus some other constant over n plus 2. Now, if I multiply all of this by n times n plus 2, it becomes 2 equals a times n plus 2 plus b times n. Okay, so when n is equal to 0, we would have 2 equals 2 times a, and then b times 0, so that reveals that a is equal to 1. And then if I let n be negative 2, I would have 2 equals, the first term would cancel, and then I would have b times negative 2, so that means b is equal to negative 1. Alright, so my series then could be written as the sum, n equals 1 to infinity, and again, the starting value of n can be anything, it doesn't have to be 1 in this case, it just so happens to be. And then it's going to be written in the form a over n, so a we found to be 1, so 1 over n, minus, because b was negative, 1 over n plus 2. And you might be wondering, do I need to have a factor of 2 here because there was a factor of 2 there? Well, not in this case. The reason is I used the 2 in the partial fractions. If I had factored the 2 out earlier and started with a 1 here instead, then I would need to make sure to put that 2 on the outside, but everything's just fine so far. And all I need to do is just plug in a few terms until I start seeing a pattern. So beginning where n is equal to 1, I would have 1 over 1, which is 1, minus 1 over 1 plus 2, so that's 1/3. And then when n equals 2, I would have 1 over 2, so that's 1/2, minus 1 over 2 plus 2, which is 1/4. Then when n equals 3, so that would be 1/3 minus 1/5, it looks like. And if you'll notice, I finally have my first term canceling. In the last example, we saw the pattern of cancellation very quickly. Sometimes it takes a few terms for it to actually show up. N equals 4, this would be 1/4 minus 1/6. And then when n equals 5, I think this will probably be enough. That's 1/5 minus 1/7. And of course, that would continue on forever. So I have a negative 1/3 and a positive 1/3, which would cancel. I don't have any matching half, so the half stays. I don't have, well, no, I do have a negative 1/4 and a positive 1/4, so that would cancel. Here's a negative 1/5, positive 1/5, and I think it's safe to say that I would have a 1/6 and a 1/7 later on, and so those would eventually cancel as well. So what that means is my sum is the sum of the terms that remain, which is 1 1/2, or 3 halves for the overall sum.